Hey, and welcome to another video. I hope you're doing well. Hope you're ready to get started on some other applications of differential equations towards populations. So, if you remember from 2 videos ago, I went through and I gave you basically a general explanation, all the theory behind population modeling as it relates to birth rates and death rates. And we did the whole thing. We talked about explosion, we talked about extinction, we talked about the logistic equation, and then I gave you a video with just a couple examples to illustrate just how to set up some basic problems with differential equations that involve populations. Now in this video, we're working our way back to the logistic equation and explosion extinction. So the way that this is structured is we did all the theory and then we did some basic examples. Now we're going to go a little bit more in depth. I'm going to show you how birth rates and death rates play into differential equations because we haven't really done that yet. We did the theory behind it, but what we haven't done is any hardcore examples about it. So we're going to talk about that right now. I'm going to give you 3 examples on how to set up a differential equation when you are given birth rates and death rates, because honestly that's the hardest part. It's just setting these things up. So I'll walk you through what to be looking for, how to use your initial conditions, how to use some sort of a change in a population to get another, to solve for your C and to solve for your K, your 2 constants that you're going to have. I'm also going to talk about how to distinguish between directly proportional and inversely proportional and what that means as far as a fraction or a product is concerned when you're going through birth rates and death rates. Then I'm going to go through and we're going to solve the differential equation. The solving part's not going to be that bad. In the next video, we're going to be talking more specifically about the logistic equation and some of these the models involving that. And so actually we have a video before that. We're going to refresh what exactly partial fractions are, because when we get to some of these harder examples, they involve a lot of partial fractions. So next video is going to be about these partial fractions, just exploring how that relates to differential equations, because man, frankly, we forget this stuff. So this is what this video is about, like really just talking about birth rates and death rates and how they affect our population modeling with differential equations. So if you remember from 2 videos ago, we talked about how logically and mathematically how the population changes with respect to time should be this difference in birth rates and death rates as proportional to a population. That's what this means. Remember, beta was our birth rate per population unit per unit of time. So like 5 births per 1,000 people per year, or whatever that is. And death rates are the same. And so we're going to look at that. But what I want you to remember is that when you're going through these, if it's not just a straight up, the way the population changes is proportional to the population itself. If they're giving you birth rates and death rates, we always really want to start here. So if they're saying the birth rate is this, the death rate is this, whatever that is, even if it's constant, you can come back and plug this in. So we know the way population changes with respect to time is birth rate minus death rate times population, that quantity times population. That really should make sense. The difference between birth rates and death rates, if it's proportional to population, shows how the population is changing over time. So we're always going to try to come back to here and say, what's our birth rate? What's our death rate? Plug it in and we have usually a fairly basic differential equation that we can solve pretty easily. So we're going to just do 3 examples. I'll model how to do this. I'll model exactly what I'm thinking about when I'm going through it, and hopefully it'll help you out in some of your examples that you have to do. So a certain population stops reproducing, but its death rate remains inversely proportional to the square root of the population. Already that's a lot of words. There were 900, whatever these things are, at the start and of our time period, and 441 after 6 weeks. When will there be none? Now, is there going to be none at some point? Well, it should make sense that if something stops reproducing, and we're assuming, remember under this from 2 videos ago, we're assuming there's no hardcore immigration or exoduses. So nothing's coming into the population that isn't being born there, and nothing's leaving the population that isn't dying there. So think about like a body of water where they're not stocking it, they're not pulling out from it. It's just the fish there are reproducing, or frogs, or whatever you want to consider. So the population stops reproducing. All right. But its death rate remains inversely proportional to the square root of the population. What we want to be looking for, because we know that this is our model for all of our population growth, rates of change of population with respect to time, involving birth rates and death rates. We want to look for our birth rate and our death rate first. And so we're reading through this going, okay, certain population stops reproducing. What's that tell you? Well, if it stops reproducing, its birth rate is 0. Well, that's nice. We can already put a 0 right there. We're going to write this stuff down. We're going to say, all right, our birth rate is 0. But our death rate remains inversely proportional to the square root of the population. Now, how would you know that? Where's that coming from? They would have done some sort of a modeling, discovering what the deaths of this species was over amount of time, and said, okay, it's really close to inversely proportional to the square root of the population. So that will be given to you. You don't have to come up with that. But it is something that we can model right now. So we figured out our birth rate. Our birth rate is 0. It's stopped reproducing. Our death rate, our delta is, let's see, inversely proportional to the square root of the population. I want to talk about inversely versus just straight up proportional. If something's proportional or directly proportional, it means that you have a product of some sort of variation constant variation, times whatever variable you have. So if we would have read proportional to or directly proportional to, that would be a k times something. When we read inversely proportional, that's going to be a division concept. So when we see inversely proportional, the first thing I want you to think of is direct proportional or just proportional means k times, and inverse means k over or k divided by. So what this is as the population is growing, the death rate is declining. That's a division concept. Can you see it? If we have a constant divided by some number that's growing, if k is a constant of variation, it's not changing, and this number gets bigger and bigger and bigger, our death rate should decline. So as the proportion, if the death rate remains inversely proportional to the square root of the population, well, that means that as the population gets bigger, our death rate should go down. And that's what this is saying to us. So again, proportional, k times, inversely proportional, k divided by. So we know that death rate is k divided by the square root of the population. Now I gotta tell you, it's really easy to do things like this. You go, oh yeah, square root. Now obviously it's not a square root, but it's really common. So make sure that we're reading this, take some time and really think about it. And go back, because if you don't have this right, the rest of your work is irrelevant. So birth rate, 0, stop reproducing. Death rate, inversely proportional, okay, k divided by what? Oh, square root of the population. So we're going to say, no, not p squared. Square root of the population. And that right there is going to set up a very nice differential equation for us. That's pretty much all you need to get started. So we have read this really clearly. The first couple sentences are typically going to fill that out for you. If you're given birth rates and death rates, you go, that's how it should look. Birth rate is whatever. Death rate is whatever. We know that proportional is k times. Inverse is k divided by. Be very careful how you're setting that up. And then we're going to substitute. Now, what about the rest of the stuff? The rest of the stuff, the initial condition, and then this amount after a certain amount of time. The initial condition is going to, make a note of this, the initial condition is going to solve for your c, your arbitrary constant, your c that you get upon integrating. The next piece, the how much you have after a certain amount of time, that will solve for your k. So putting this whole thing together, your population change with respect to time, dealing with birth rates and death rates, will be modeled on that. Find your birth rate and your death rate in terms of p, or a constant. That's fine. If it says held constant, great, just put a k. That's okay. Plug it in, solve your differential equation, and then as soon as you integrate, then use your initial condition to solve for c, and then use your later condition, so this population change after a certain amount of time, to solve for your k, and then you can answer any question that you want. So we're going to try that right now. So we've looked at, we said that's it, okay, we got our birth rate, we've got our death rate per unit of population, per unit of time, and now that lets us substitute into here. So we're going to have this population change with respect to time is the birth rate minus the death rate times the population. We've just plugged this in, 0 k over square root of p times p. And we can simplify this. This would be negative k square root of p. Or if you want to write it better, the 0 minus this, of course we have a negative, k p to the 1/2 would be fine as well. That's totally fine. It really doesn't matter. Now, what do you see? Well, we see the reason why we practiced about 30 videos of just doing differential equations because this is going to be something that falls into one of those categories. This is a separable differential equation. So we are going to group our p's dp on one side and our constants d, whatever that other independent variable is, in this case t, on the other side. So k is a constant. We're going to leave negative k where it is. That's a constant. We said that's a constant of variation. And it's going to be found by using how our population is varying. So let's move our p's dp. That'll be p to the negative 1/2. We divide both sides by this p to the 1/2. We would say that population can't be 0. Obviously, the population not going to be 0. There's a really boring problem. We get just a singular solution there, so it wouldn't be very, very good. And then on the right-hand side, we'd have our k dt. I hope that makes sense. I'm going to go fairly quickly through some of these basic integrals that are in solving differential equation techniques like separable equations, because we've done it just a heck of a lot of times. So get your p's dp, get your constants dt. Let's integrate both sides, and notice that on the left-hand side, I'm adding 1/2, dividing by 1/2. That's going to be 2 square root p equals negative kt plus your arbitrary constant. Now, you're going to want to solve for p, and I know that you want to do that right now. But I'm going to tell you that when you start solving for p, it's a whole lot harder to find your c and your k in general as you keep moving forward. So as soon as you can, you want to solve for the constant and your k, so both of these constants. Why we couldn't do it here, because I think I gave you an example a long time ago, like last video, where you could, because they gave you the rate at which the population is changing. You're not generally going to be given that. So we don't know what that rate is. What we do know is we know that our initial population was 900 at time 0, and we know that there were 441 after 6 weeks. So that's something that we really should write down. And I did all this work first, but you might want to consider writing it up here first. So on hindsight, I would say find your birth rate, find your death rate, find an initial condition. So what happens at time 0? When we started this situation, this observation, there was 900 units of whatever this species was. And after 6 weeks, there were 441. That's something we might want to write down first. Now, I didn't, just to show you that this cannot be used here. Do not start plugging this junk in, please. Wait until you integrate and get right here. So, again, all the way through. That's going to be your population change with respect to time if you're dealing with birth rates and death rates. So when we go through this, we read it very carefully. Find your birth rate and find your death rate. Then write down your initial condition and how much your population is after a certain amount of time. That's how the population has varied. Keep that in mind. We use our knowledge of differential equations to plug this in and simplify and solve the differential equation. And then right here, as soon as you integrate, give it a try. Try solving for your c and then solve for your k in that order. The reason why it's got to be in that order is because your initial condition is going to plug in 0 for t and kill off that k, which you don't know. If you try to solve for k first, you'd have too many variables that wouldn't really work that well. So plug in your initial condition, time of 0, and a population, and it's going to solve for c very nicely. Then plug that in, turn right back around, and use that, how your population has varied, to solve for your constant of variation. So let's try it right now. So we've done our integration. We go, okay, right here, don't solve for p. You'd have to undo everything to solve for c if you did that. Let's plug in p of 0 equals 900. So p of 0 equals 9, let's see. That means that this is going to change to 2 times the square root of 900. So when t is 0, we had 900 units of population. We don't know what the k is, but that's fine. That's why we're using the initial condition first at time of 0, because that's going to do 0 times any constant, give you 0 plus c. And if we do all the work, 2 times 30 is 60, so c is 60. Take that constant and use that right now to rewrite this. So we know that 2 square root of p equals negative kt plus 60. So all we've done is we've done our solved our differential equation and then solved for our arbitrary constant like we've done many times with initial conditions. That's what your initial condition does. It solves for your arbitrary constant. Then we're going to turn right back around as soon as we can and solve for that k. So we need to find that out as well. The constant of variation is typically found how your population is varying after a certain amount of time. So once we found our c first, 0 because it kills off that k, then we're going to say, all right, well, at time 6, and we're going to keep in the back of our mind that this means 6 weeks. At time 6, we had 441 units of population. Okay, all right, so let's see. We had 441 units of population after 6 weeks, and because we solved for our C, that's not 60, because we solved for our C, we're now able to solve for that K. So doing just a little bit of math, square root of 441 is 21, I believe. So 2 times 21 equals, well, that's negative 6k plus 60. And that's really easy for us to solve. It says, let's just multiply. It's going to be 42. We subtract 60 from both sides, we get that 18, but it's negative. And then k equals positive 3. So k equals positive 3. That means that our, let's think about that. So our death rate was k divided by the square root of p. So that means as the population's growing, that death rate is declining, but it's still positive. Things are still dying. Now we can plug that in and solve for p. So we've done everything. We found our arbitrary constant. It was 60. We found that our constant variation was 3. We sort of have an idea about what that means. And now when we substitute that in, we know that 2 square root p equals negative 3t plus 60. Now question. Do you understand how the birth rate and death rate was found? Do you understand how the initial condition solves for the arbitrary constant? You should know. And how the population varied is how we find the constant variation. Once you've done that, really, these are application problems. So these are looking for an answer. They're looking for an answer to some question. When will there be none? In other words, when, that's a time, will the population be 0? Should kind of make sense to you that if the birth rate is 0 and the death rate is positive, which we see that it is, that k is positive, and the population is positive, so your death rate is positive, that if your birth rate is 0 and things are still dying, you're eventually going to have nothing. So if that birth rate doesn't change and the death rate is held to be what this is, your population is going to die off. There will be none. So when is that going to happen? When's the population 0? It's very tempting to solve this for p. I know, it's really tempting to be like, okay, I got to divide by 2, I got to square both sides. Why? Why do that? If we're trying to find out when, that's a time. Now, unless it says specifically solve for the population model, well, you could do that. You could divide everything by 2, square both sides, and you find the population based on time. But if we were asking this question, and that would look like this. So dividing by 2, negative 3/2t plus 30. And then square both sides, and you could get the population model based on time. That's totally fine. If they ask you a different question, like what's the population after 9 weeks or whatever weeks they want, good. That's totally fine. But if they're asking when is the population going to be 0, well, that's trying to solve for t. So if we want to solve for t, does it benefit us to solve for p? Not really, because we'd have to undo all of that work anyhow. So if you want to find out t, when the population equals 0, and that's what we're asking, right? When is the population 0? It's a lot easier to plug in 0 here and solve for t than plug in 0 here and solve for t, because you'd have to undo all of the work you did in solving for p. So I'm going to do that from right here and say, all right, well, that means that if our population is 0, it's supposed to be a 0, then we're going to have negative 3t plus 60 equals 0. Adding 3t to both sides and dividing by 3. 320. What's that mean? That means, and we think back to what this says, what the variation told us here. This population varied, and so that we went from 900 to 441 in 6 weeks. So that unit of time for t is given to us in that problem somewhere. So that says that according to this modeling, the way that this population is changing is that there's going to be none left. Unless something changes, there's going to be none left in 20 weeks. I'm trying to make this as streamlined as possible so you understand exactly what you're looking for, because word problems, we all know this, word problems can be a real bear, and mostly it's the setup. So when you're dealing with population models, I did all the theory 2 videos ago. I did some very basic ones last video where we said, okay, population, the rate of change of population with respect to time is just proportional to the population somehow. Now when we start dealing with death rates and birth rates, we're going back to a previous video saying all of them should be able to be modeled like this. So find your birth rate, find your death rate in terms of p or constants. Then you have a differential equation that's typically okay to solve. You solve that differential equation. Right away, use your initial condition to solve for c, and if you can, use your how the populations vary to solve for your constant variation right after that in that order. And then we can answer virtually any question they ask us. We can solve for the population model. We can solve for when the population is a certain amount. We can solve for what the population is after a certain amount of time. I hope that makes sense. So I'm going to come back. We're going to do 2 more examples. I wouldn't say they're any more difficult, but we're going to have a different birth rate than 0, and we'll see how that works. We'll talk about how if you have a birth rate and a death rate that is based on a constant of variation, they're not the same constant variation. We'll explore that in just a minute. Let's try another one. So we have a certain population, and it has a birth rate and a death rate that are both inversely proportional to the population. At the beginning, when we first started the observation, there was 100 units of whatever the species is, bunnies or something, and then 169 after 6 months. So it's growing, obviously. The birth rate should be outpacing the death rate. How many within 1 year? All right, well, what do we know? We know that because we're given birth rates and death rates, the way the population is changing with respect to time, the rate of change of the population with respect to time, should be based on a difference between birth rate and death rate times the population. So we discovered that 2 videos ago. Now we're just exploring that. So let's first look for, and I've left this on purpose because this is the model behind a lot of these problems. Let's look for the birth rate. So it says the birth rate and the death rate are both inversely proportional to the population. So, man, do you remember what inversely means? Inversely means k divided by, so a constant variation divided by. So the birth rate is inversely, that's k divided by, proportional to the population. Oh, you know what? I meant to write square root. Inversely proportional to square root of population. And the reason why I wanted that is so I want you to consider the difference between this problem and the last problem. Last problem, birth rate was a constant 0, and death rate was proportional to the square root of the population. Now I want to consider what happens if both of these are proportional to the square, inversely proportional to the square root of the population. So last time it was just the death rate that was inversely proportional to the square root of the population. This time it's both birth rate and death rate that are inversely proportional to the square root of the population. So sorry about that. So the birth rate is inversely proportional. That's k divided by the square root of the population. All right, well, that's the square root of p. Well, wait a minute, the death rate's the same. The death rate is inversely proportional, k divided by, to the square root of the population. Now, if we try to put this in here, we know that the way the population changes with respect to time is birth rate minus death rate. Okay, we got that. We read through this. We know that the birth rate and the death rate are both inversely proportional, that's k divided by, to the square root of the population, that's divided by the square root of p, and we can substitute this in here. That would be k over square root p for the birth rate minus k over square root p for the death rate times p. And you go, that's 0. And you would be right if they were the same constant of variation. You go, how can they be different? Well, your birth rates and your death rates aren't always the same. And in fact, if our population is growing, look at that. We had 100, then we had 169. Your birth rate is outstripping your death rate. So these Ks can't be the same, otherwise our population wouldn't change. We just get 0. And the rate of change of your population would be 0. And after 6 months, you'd have 100. After a billion years, you'd have 100. It wouldn't change. And so our birth rate and death rates can't be the same, hence these Ks are different. And so to show that, go, you know what, this is K sub 1 and this is K sub 2. And that was showing that your birth rates and your death rates don't have to be the same. In fact, they can't be if our population is growing. So we've gone through, we've understood what our birth rates and death rates are. We were very careful writing those. We've made our substitution. We now have a differential equation that we're going to work with in just a minute. But before we go any further, we're not going to use this information yet, but we're going to write it down right now. We're going to write down the initial condition. So there were 100 at time 0. And after 6 months, so how our populations varied, after 6 months there were 169 of this particular species. We want to write all that down so that we're completely done with this problem. We should do our math, okay? So we look at it and go, birth rate got it, death rate got it, substitute it. Now let's solve our differential equation. Before we go any further though, write down our initial condition and how our population is varied after a certain amount of time. We're going to use this as soon as possible, right after we solve our differential equation. So what in the world can we do? Well, because both our birth rates and death rates are based on being inversely proportional to the square root of that population, it's given us a common denominator. We can combine this. So k sub 1 minus k sub 2 all over square root of population times the population. And you can see right now we're going to do basically the same thing. We're going to simplify this square root population. One other thing you're going to see a lot of, is it true that a constant minus a constant gives you a constant? Is that true? Yeah. And so a lot of times what we're going to do is we're going to take this different constants of variation and say, you know, since we're based on the same inversely proportional to the square root of the population idea, we can define a different k to stand for that constant. And that makes our math a little bit more concise. It's not going to affect your problem at all. All it's going to do is make it a little bit nicer when you start plugging in numbers, your initial condition, and then your constant variation information. It's going to make it a little more succinct. And so let's go ahead and make this a differential equation with respect to time. And we'll have k square root p, just like we had before, but notice no negative right there. You also could make this just like before, just like the last example, k times p to the 1/2 power. And now we have something that's separable. You really should try this from here on out. So get your p's dp, your constants dt, integrate. Plug in your initial condition right after you do that to solve for your c. Then plug in your varying, or the information on how your population is varying to solve for your constant of variation right after that. And then we'll see what we have after that. So p's dp, k constant dt. If we integrate, we get exactly the same thing we did before. There's 2 square root p. And then on the right-hand side, let's see, we get this kt plus c. Now I want to talk about something real quick before we get, I told you that right now we were going to do it in just a minute. I'm just going to give you a little aside here. We're going to plug in our initial condition, we're going to solve for our C, then we're going to plug in our how our population is varying to solve for our K. But once in a while, you're going to be asked to show something. So if you're ever asked to show what the population model is based on an initial condition where the initial condition is changeable, what do you mean? What if I didn't tell you there was 100 items? What if I wanted to move this model to different populations with the same species? So in other words, yeah, this population started with 100 whatevers. But what if I wanted to model this on a different population where we knew the same dynamics, the same dynamics were going to happen, but that initial condition was like 1,000 or 1,500 or 2, and we knew the same things was going to happen? Well, then oftentimes what we do is we say, if I don't know an actual initial starting population, so the initial population, if I don't know that, I call it p sub 0, and then your constant will be based on that p sub 0. And so how we would show this, we'd say, all right, I'd plug in 0 for t, I'd plug in p sub 0 for p, so there'd be 2 square root of p sub 0 equals 0 plus c. And then we can have something that's at least we have this arbitrary constant we can write up there. So c would equal this 2 square root p sub 0. We go, all right, if I want to solve this now, 2 square root p would equal k times t plus 2 square root p sub 0. And we can solve for that arbitrary constant in terms of an initial population, whatever that population happens to be. Then what we can do after that, well, we can't really solve for k, can we? Because in order to solve for k, we need to know an initial population. And so what you could do here is just say, well, if I wanted to solve for the population model, I'd divide everything by 2. And square both sides, and we can find a model for the population. But notice, you would need to know some more information before you go any further. So we said, can you find out a population model? Yes, but to get more specific, you need to know about a specific population. You would need to know the initial population, and you could just straight up plug it in right there. That is the initial population. So if we move to a different area, want to apply this model to a different population, we need to know where we start. And then we'd also need to know how the population is varying after a certain amount of time. So initial population would go here, but to solve for that k, you need to know how the population is varying a little bit after that. Then we could get more specific, but at least we can find a population model right now. So could you plug in 100 right here? Yes. Could you plug in 6 for t and then population of 169 and solve for k after you've done that? Of course, it's a lot harder to do from there, but if we are going to apply this model to some of the population, that's nice to have because we can now plug in different specific starting and changing points in that population and get a working model from it. I hope that makes sense to you, that we can still solve this for p, we just have a couple arbitrary, well, not arbitrary, we have a couple constants in there that would be based on whatever population we're dealing with. So can you still solve for p? Yes. And get a model, of course, that's based on initial population, and somehow a constant of variation. Yeah, you can totally do that. What I'm going to do is I'm going to erase this, I'm going to come back up here, and then we're going to do what this particular problem is calling for. We want to find out whatever our c is based on this initial condition, whatever our k is based on how our population is varying after 6 months. So we're going to do it and answer this particular question. So right here, we'd say, why solve for p if we're dealing with this one population? We would say that the population is 100 at a time of 0, and we would get c as 20. No problem, plug that back in. We now know c. And because we're solving for k, and we were able to plug in 6 for time and 169 for population based on how that's varying, let's see, 2 times 13 is 26. Six equals 6k. K is a very convenient 1. And now we're able to plug that right back in. You know what? I said it here, but we really are plugging it here. We found that C already. So one time, all the way through, we look for birth rate, death rate. We know that that is how our model should be. We plug it in, we do our substitution, we get this differential equation. We know that we have a constant variation that we can combine a couple constants if possible. It's not a problem. We solve our differential equation. If we need to solve for p, I showed you how to do that with an initial population. If we don't, if we're answering specific questions about a specific population like we are here, find your c first with an initial condition, find your k second with how the population is varying, and then we have this model. 2 square root of the population equals time plus 20, where time is in months. And now we answer the question. We're going to say, or we're going to see whether it's going to benefit us to solve for p or not. So, how many is there going to be in 1 year? How many? How many is a population after a certain amount of time? So, would it benefit us to solve for p? Yeah, it would, because we're trying to solve for the population anyhow. So let's divide everything by 2, and let's square both sides. So divided by 2, we get t over 2 plus 10. Square both sides, we get t over 2 plus 10, quantity squared. This is the population based on a given time. Now, we're going to find the time after 1. So we plug in 1, right? Be real careful. If this is in 6 months, we're going to plug in 12 because 12 months is 1 year. So the population after 12 months is 12 divided by 2 plus 10, and then we square it. Our population after 12 months, 16, so 256. So 256, whatever this species is. Man, I hope that makes sense. I hope you're seeing the interplay between birth rates and death rates, that if you have two constants of variation, they are different. Otherwise, your population won't change. It generally won't change if you're based on the same way you're varying with the population. So could they be different proportionalities? Yeah, they can, and it would change even if those constants are the same, but you can't assume that they are the same. I hope that makes sense. You don't just assume there's the same constant of variation. In this case, your population wouldn't change at all, and we know that it's growing, so that can't work. So I hope it makes sense. The integration should be very nice for us right now. The separable differential equation should be really, really nice. And then knowing when to plug in for your constant c and when to plug in for your constant k is crucial. So we got one more. We're almost done. I'll be right back. Last one for the video. So we're dealing with another population. I know I've had the same thing 3 times, but we're dealing with this slightly different way. I want to show you in this example that because we have proportional, we're not going to have a k divide, we'll have a k times. We'll talk about a doomsday versus extinction here. So I want to show you how the k being positive will lead to a doomsday or a population explosion is what we call that. Or if our k would be negative, we deal with an extinction scenario. So I want to show you where that comes from. So let's explore this. Let's pay attention to that last little bit. I'm going to solve for p. I'm going to show you the model here, the population model based on k and the initial population, and then we'll deal with this specific example. So certain population has birth rate and death rate that are both proportional to population. There were 6 when we initially saw it and 9 after 10 months. When will a population explosion happen? How do I know there's going to be a population explosion? Well, proportional is climbing and climbing and climbing, but if our population has grown after an initial condition, that means our birth rate is outstripping our death rate, and it's going to explode at some point based on that proportionality. So we're going to see that at play right now. So we've read through it. We're going to go ahead and we're going to say, all right, hey, this is dealing with birth rates and death rates and a changing population. Let's try to model it with this. Our birth rate says proportional to population. When you see proportional, it means directly proportional or varies directly. It means k times. So our birth rate is k times population. And so is our death rate. It says they're both proportional to the population. So we're going to call one case of 1 and one case of 2. And now we're ready to go ahead and find our initial condition and how our population is changing after a certain amount of time. So how do we start? Let's see. There was 9 at the initial observation. So at time 6. There was 6, whatever these are, at the initial observation. After 10 months, so we're in months here, there were 9. Certainly doesn't seem like there's going to be a population explosion, right? Like after 10 months, there's only 3 of them. But it will happen eventually. Now that we've found our birth rate and our death rate in terms of our population, now that we have our initial condition and how our population is varying after a certain amount of time, let's substitute this and find a differential equation that models it. So we know that our birth rate, case of 1 times population, minus our death rate, case of 2 times population, times population. Now, it might be a real good idea to factor out that p. Sort of what we did before, and we simplified it with the p. So let's do that. If we factor the p, we're going to get case of 1 minus case of 2 times p squared. It doesn't cancel, we get p squared. Now, let's redefine it like we did before in the last example. Let's say that instead of case of 1 minus case of 2, let's call this k. And I want to make an important point here. Based on what those k's are, determines whether you are going to have an explosion or an extinction in this particular case. If that k is positive, you're going to grow, and the change in population will be positive and grow, 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 grow. This can't be negative. Grow, 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 grow without bound. There will not be a bound here. You will get a population explosion. They call that a doomsday because at some point, population is just so massively large, there's not going to be enough space or food or whatever for this particular species. If that k is negative, then this would decline and always decline. Decline, 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 decline. It would go to 0. That would be an extinction event. And so we'll see that right now. So wait a minute, wait. How would the k be positive? That k would be positive because these are the same population at the same time. That k would be positive if the birth rate is greater than the death rate. That's the only way that could happen. So the only way that birth rate is different from death rate here is if the k's are different. So the k will be positive if birth rate is greater than death rate. K will be negative if birth rate is less than death rate. It's the only way that's going to happen. We're going to consider both of those in just a minute, so hang on with that. So we're going to call this k, we're going to solve our differential equation. We're going to group our p's dp, our constants dt, and we're going to integrate. So on the left-hand side, we're going to add 1, divide by -1. So -1 over p. On the right-hand side, we're going to have a kt plus c again. And I'm going to do 2 things. I will be coming back to this and using it, but because I want us to explore extinction versus explosion, so explosion versus extinction, I want to solve this for p the way it is. So I'm going to do a little aside right here. We're going to talk all the way through that. Then we're going to see this actually happen with this information. So if we solve that for p, the first thing I might want to do, if I'm going to solve that for p, man, I might just solve for the constant right now, this arbitrary constant, by saying that at time 0, I'm going to have an initial population. So you'll notice I do this a lot, right? I solve for that arbitrary constant c like every time if I can. And it's always going to end up being some form of an initial population. So I'm going to plug in 0 for t and p sub 0 for p based on this right here. So p sub 0 for p at time 0 lets us solve for c. We know that c is -1 over p sub 0. Let's plug that back in right there. Okay, now what? You know, I don't like that negative. Maybe we change all the signs. Also, I know I'm going to try to reciprocate this, so yeah, we're going to need to find a common denominator. So we're going to multiply this by p sub 0 over p sub 0. These are the same. I've just multiplied p sub 0 over p sub 0. Now that we have that common denominator, we're going to combine that fraction. And we've written this in out of order. So 1 minus p sub 0 kt, all over p sub 0. And if we reciprocate both sides, so if you think about cross multiplying, dividing if you want to, our population due to time is based on the initial population divided by 1 minus the initial population times k, constant variation, comparing the birth rates and death rates, times t. Now, I need you to see this. If your k is positive, notice how your time is always positive and your initial population is always positive. Otherwise, this is a meaningless problem, and if your initial population is 0, then this will all be 0, because it'd be 0 divided by 1 minus 0. You would get you would have no population. How could you have a population after a certain amount of time if you don't start with a population? Doesn't make sense. So if our k is positive, stick with me. If our k is positive, that means our birth rate is greater than death rate. Our population should be growing, right? If our k is positive, that means that we have a positive here, a positive here, and a positive here. 1 minus that number is going to get smaller and smaller and smaller and smaller and smaller and smaller and smaller, while your initial population, that number doesn't change. That's a constant. So remember, that was c, right? That came from c. So if you have a constant being divided by a denominator that's shrinking, you are going to get a population explosion. Do you see the math? The population approaches infinity as t approaches infinity if k is a positive number. So actually, no, as t approaches, what would that be? Because we want this to get closer to 1, right? So if t is approaching 1 over p sub 0k, if t is approaching this number, then look at that. If t is 1 over p sub 0 times k, this would get closer and closer to 1. Think about it. If this is getting closer to 1 divided by p sub 0k, then this is getting closer and closer and closer and closer to 1. Then 1 minus that number is getting closer and closer and closer and closer to 0. Then constant over something that's getting closer and closer to 0 is getting really close to positive infinity. So if k is positive, one more time. If k is positive, it means birth rates are greater than death rates. That means k is positive. That means that this is getting really close to 1. This would get really close to 0. This whole fraction would get close to infinity, positive infinity. That's a population explosion. That t, as the time approaches that value, 1 over p sub 0 times k, whatever that happens to be, that's when you are going to get the population explosion. I'm going to show you that in just a minute. Promise I'm going to show you that with actual example in just a minute. Now, what if your k were negative? I told you I was going to talk about this right now. So what if your death rate is outpacing your birth rate? That would mean birth rate's less than death rate. Your k would be 0. If your k is 0 here, that would be k is negative. If your k is negative, that's a positive and a negative number. 1 minus a negative is a positive. This would be growing and growing and growing and growing. And as t approached infinity, after a long time, well, whatever that is, as t approached infinity, this number would be getting bigger and bigger and bigger and bigger and bigger and bigger. This number would stay the same. Your population would go to 0. Are you seeing it? So if your k is positive, then as t approaches 1 over p sub 0k, your population is exploding. But if k is negative, then as t approaches infinity, k is negative, you're subtracting a negative. If that can't change, and that can't change, and that's the only thing that's changing, then as t approaches infinity, this approaches infinity, your fraction approaches constant over infinity, constant over something approaching infinity, would give you something very close to zero. Your population would approach zero. This is the difference between an explosion and an extinction. It's all based on your K in this case. So this says, yeah, hey, if your birth rate, man, it's got to make sense. I mean, are you seeing it? Are you saying if your birth rates are bigger than your death rates, you're going to grow, obviously. You're going to grow. How much you're going to grow is based on whether you're bounded or not, logistic or not. Here we're not bounded by anything. You're saying this shows you you're not bounded. This says that as your K is positive and your T is approaching 1 over P sub 0 K, you're getting really close to zero here. And when you're getting close to zero, your constant divided by something close to zero is exploding. If your K is negative, so your birth rates are less than your death rates, then that's a negative number. And as T approaches infinity, you're saying 1 plus some number that's going to infinity, a constant divided by some number going to infinity, it's going to go to zero. You're going to get extinction. I hope you're seeing that. I hope you're seeing the interplay between like a calculus 1 idea, like going to different infinities as your T approaches different numbers based on a constant that's positive or negative. That's a calc 1 idea, but it's so interesting to see this with populations. It's really interesting to see why we get population explosions and why we get population extinctions mathematically. Logically, it makes sense. Birth rates are greater than death rates. Birth rates are less than death rates. It makes sense. But seeing that mathematically with your limits is pretty neat. And that's exactly what we're doing. So I'm going to erase this real quick. And what I'm going to do is we're going to now use this information. And I'm going to show you why that works. I'm going to show you what this does. So coming back up here and saying, hey, you know what? Now that we have this negative 1 over P equals KT plus C, and saying, hey, how do I solve for a C? My initial condition would do that. So the population is 6 when my time is 0. C is negative 1/6. Wait a minute. C is negative 1 over the initial population. Yes, it is. Okay, so negative 1 over P equals K times T minus 1/6. We can now use how the population is varying to find our constant variation. So when the population has had 10 months to grow, we have 9. You know what, let's go ahead and add 1/6 right now. So let's see. Negative 1/9 plus 1/6. Negative 2/18 plus 3, it should be 1/18. And if we divide by 10, K equals 1 over 180. Wait a minute, didn't we say the K should be positive here? Yes, in fact we did. We said that because our population is growing, it should make sense that the birth rate has outpaced the death rate. So the difference between those two needs to be a positive number. And in fact, that's what we have here. So we know right now, based on what we just learned about this, that if our K is positive, we are going to get an explosion. We'll be able to answer this question. We are going to get an explosion. We just talked about y versus the limits. We talked about how if we're taking a constant, they're both positive, and the t is getting closer to 1 over that number, you're subtracting 1 minus something close to 1. You're going to get something close to 0. You're going to get a positive explosion there. It's going to go to infinity. This shows that our K is positive. Now let's rewrite that. So we're going to put this right here. Like before, just like we did over there, let's change all our signs. So change the sign positive, change the sign positive, change the sign minus. I've made this t over 180. Let's get a common denominator. So let's see, that would be multiplied by 30. If we make one fraction there, we're going to get this 1 over p equals 30 minus t over 180. reciprocate. And we have a specific function that models this specific population. Now, use your Calculus 1 brains and think about this for a second. As t gets closer to what number will this population go bananas? As t gets closer to, look, you're subtracting. So 30 minus, let's say 0. 30 minus 0, you should get 6. Huh. 30 minus, let's say 10. 30 minus 10 would give you 20. 180 divided by 20 would give you 9. Oh my gosh, it works. Now, what if we did 30 minus, like, how about 30 minus 29? 30 minus 29 would give you 180 over 30 minus 29 would give you 30 divided by 180 divided by 1. That'd give you 180, whatever the species is, after 29 years. 29 months. 29 months. What about 29.9 months? So 29th month is pretty important. So at 29 months, we're 180, whatever these are. At 29.9, you have now 180 divided by 0.1. That's 1,800. What about 29.99? That'd be 0.01. That's now 18,000. So as t approaches what month is this exploding like crazy? Well, as t approaches 30, you can see it right here. This is a positive number. As t is climbing, it's going to get closer and closer and closer and closer and closer to 30. It's going to get closer to that. Well, as it's getting closer to 30, as time goes on, time starts at 0, it goes positive, then this is going to start exploding until we hit 30, and then we get an infinity, an undefined idea. We can't get past that. So right here, as t approaches 30, our population is approaching infinity. Now, I told you that was gonna make sense. You go, can we think about that? What is 1 over p sub 0 k? P sub 0 was 6. K was 1 over 180. P sub 0 is 6. K is 1 over 180. If you do that, let's see, 1, let's multiply, let's just, that's a complex fraction, so t would be 180 over 6. T would be 30. As t approaches 30, that is going to go to infinity. We showed it. We just showed it right here, and now we see that. We see it in the math. We see it as a formula, if you want to call that a formula. But I want you to logically understand what we've talked about. I want you to understand that if your k is positive, as your t goes to infinity, you're going to get explosion with these cases. If your k is negative, we're going to get extinction. So if this was like a 6 and this was like a 3, your k would be negative. Right here, you would see that as t approaches infinity, you're going to go to 0. You can try that for yourself. But man, that's kind of cool. If you want to see the exact model of that, if you want to, it doesn't look exactly the same, Leonard, we can get the same thing by doing this. If you divide everything by 30, then divide 1 over 30, 1 over 30. I know you can't read that. So that would be 6 over 1 minus 1/30th t. As t approaches 30, 1 over 30 times something approaching 1 over 30 is getting really close to 1. 1 minus something really close to 1 is getting close to 0. 6 divided by something really close to 0 is getting really close to infinity. Try the other one for yourself. Do one where your population is decreasing like this. Call that a 3. And see what happens. See what would happen. Just for fun. Be a 1/3 right there. 1/3 plus 1/6. So negative 1/3 plus 1/6. Negative 2/6 plus 1/6 is negative 1/6. multiply by 10, you get k equals negative 1 over 60. And right there we see the negative k. We know what's going to happen. We're going to get an extinction event. This would be, let's see, so still positive 1/6, but we would get a positive t over 60. Then this would give us a ten plus t over 60. Getting a common denominator, you'd have 10 over 60. So 10 plus t over 60. When we reciprocate that, we get straight up right there. Let's see if that works. Yeah, if we divide everything by 10, that'll fit this model. So if you want to do that, you can divide everything by 10, get 6 equals 1 plus t over 10. And that would say your initial population, 6. Why is that? Why is it plus? Should be minus. Nope, because your k is negative. That changed that. So I'm going to go back up to here. Just because it's easier to see your limit right now. So take a look, man. This is icing on the cake. Pretty cool. What's happening? What's happening? Your initial population starts at 6. I can change this to see the 6. That's not a big deal. We're looking at it. As your t gets bigger and bigger and bigger, what's happening to this fraction? Well, that's staying the same. This says I'm not subtracting anything. As t moves forward, t of 1, well, let's put 10 in there. T of 10, maybe? T of 0 would give you 6. T of 10 would give you 3. 60 divided by 20 is 3. How about 4? How about 11? How about 12? How about 13? How about 14? How about 15? How about infinity? As t gets bigger and bigger and bigger and bigger, we're dividing 60 by something that's growing positively larger and larger and larger. You have a constant over something going to infinity, that's going to go to 0. And now we've explained both of these ideas with actual numbers. I hope that makes sense. I hope you're seeing the interplay between the limits of like Calculus 1, these populations, and these differential equations. This is awesome. This is really cool. So I hope you've enjoyed it. I hope I've made some of these population models understandable for you as they relate to birth rates and death rates. I'm going to see you for the next video where we're just going to talk about partial fractions, because in the next video after that, we deal with a lot of them. So get prepared for it. If you don't need help on partial fractions, feel free to skip it, but I will show you how they relate to differential equations. So I'll see you for the next video on that.